name is Jacob. I'm a senior in the physics department. I'm going to talk a little bit today about my research relating to earthquakes. First, a little on the motivation for why we do this kind of research. Consider, for example, the 2011 Tohoku earthquake off the coast of Japan. It was enormous, magnitude 9.1. Killed some 16,000, injured thousands more, and was, by a large margin, the costliest natural disaster on record. It actually moved the entire main island of Japan 8 feet east. Given the catastrophic nature of these events, it would be really nice if we could predict when they might occur. However, earthquakes are notoriously difficult to predict. Some might say impossible. So I take a computational approach, which means I don't actually look at real seismic data except to compare, make sure that my simulation gives realistic data. There are two main advantages to the computational approach. The first is that it is much faster. Modern seismology has existed for only about 100 years, and earthquakes are relatively infrequent on a human timescale. So the only way to get more data is just to wait for earthquakes to happen. On the other hand, using simulations, I can run a simulation in about a day that corresponds to that 100-year history of seismology. That's very helpful. The other major benefit is that we have complete control over the parameters that govern the system. So you can change one thing, two variables, and test how the system responds to that change, and see if it corresponds to your predictions and what happens. You can test it against your theoretical predictions. We take a statistical approach, so we're not trying to reproduce any particular fault system. We're trying to go very general and figure out what are the bare minimum physics that we need to get out this earthquake behavior. Now, we know a few things about earthquakes. We know they're not completely random. They're clustered both in space and in time. They also show this very interesting characteristic, which is called Gutenberg-Richter scaling. The basic relationship is between the number of events, earthquakes, of some particular size in relation to that size. What it basically means is that we have a whole bunch of very small events and very, very few big events, as you might expect. But what's really interesting is that, for example, this is for global seismic data, all the earthquake data all over the world. But you can look at any particular fault and plot the same things and get the same relationship. It doesn't matter what scale you look at. It's always this nice straight line power law behavior. So, onto the model language. First things, this, you might think you're looking at an aerial view. You're not. If you consider two tectonic plates sliding against each other, what you're looking at is a cross-section between them where they press against each other. Okay, this is what we call a cellular automaton. It just means we have a bunch of individual cells or sites that work together. So, we initialize this system, typically square. We don't use things this small in practice, but it's good for demonstration. And we say that every site in this lattice has some stress value attached to it. We pick a random value to start with. It's in between what we call a residual stress threshold and a failure stress threshold. Those are your sigma R, sigma F. Then you have this d sigma, not a differential for the mathematicians in the room. This is just some little amount of stress that we add to every site. It's the same for every site. Alpha is sort of a mysterious factor that has to do with energy leaving the system. R is a stress transfer radius that we'll come back to. In this model, the size of an earthquake is given by the number of sites that fail on any given time step. So if 5 sites fail, the size of the earthquake is 5. So let's walk through the process. After we've initialized the lattice and everybody has some starting stress value, we run through, and on every individual site, we increase the stress by some constant amount, that d sigma. Then, we scan the entire lattice one by one and check, did anybody fail? Does anybody hit that failure threshold? So let's say we've got this one that's at the failure threshold. We say the site has failed and that the site is broken. So the first thing we do is where that alpha parameter comes in. We throw out some stress, some energy from the system. We typically think of it as heat or sound. Then we look in a radius around that failed site, and any stress that remains on that site, we distribute evenly to everybody in that radius. And and then we drop that failed site back down to the residual level. You can think 0. But then we have to check again. Did any sites fail because of that distribution of stress? So let's say we have 2 more sites that failed because of that. So we have to run through this failure process again for each one of these. So we have to scan the lattice, find out who failed, and then do that whole process again, over and over again, until no sites are above the failure threshold. And then when there are no sites above failure, we start at the beginning and increase the stress on every site. Okay, so the first thing when we build a model like this is we want to know, does it give data that's consistent with real earthquake data? This is that Gutenberg Richter for global seismicity I showed you a minute ago. And this is Gutenberg Richter scaling produced by the model. As you can see, we get that nice straight line power law behavior. You might wonder what's going on at the end, but we don't have time to go into that. Here I will draw your attention to, this is the size of the earthquake at any given time step throughout the run of the simulation. I just want you to note that it's pretty red. There's no noticeable patterns in here. Now, you might wonder, does it make sense that every site in the lattice has the same failure threshold? Or put another way, that in this tectonic plate system, is every bit of rock equally strong as every other bit of rock? Probably not, right? Okay, so we introduce what we call asperities. These are just strong sites. We pick 1% of the sites at random and decide that, for example, they have a failure threshold 10 times greater than everybody else. When we do this, remember I said, earthquakes are not random. They're clustered in space and time. So when we add asperities, we get that cluster. This little red star you can think of as the 9.1 earthquake off the coast of Japan. That's your main shock. It's preceded by a gradually increasing number of large events and a gradually decreasing number of large events. Those are the foreshocks and aftershocks. So that's some behavior we want from our model. That's consistent with real earthquake data. Now what's more interesting when we add asperities is that the size versus time graph that we looked at a minute ago becomes completely rigidly periodic. Now, if earthquakes were really this periodic, we would have no problem predicting them, but that's not the case. But it is interesting. The shaded area in the background corresponds to when an asperity site broke. So as you see, when an asperity site breaks, you get a really big earthquake. And the spacing, you can just tell, between the spacing that corresponds to the time between events, is the same all the way through. So as it turns out, the time between those major events is directly proportional to the strength of the asperity sites. Now you might again ask the question, does it make sense that all of the strong sites in this system are equally as strong? Again, probably not, right? Okay, so what if we add 2 distinct asperity thresholds? Here again, you can see that we've got this characteristic spacing. That corresponds between these really big events to one asperity site. That's the red shading on this graph. This is the same graph, just this one showing you when an asperity site's broken. But if you look down here, you see we've got this other characteristic spacing. And that corresponds to the blue shading here. That's the time between the smaller asperity sites breaking. So, we introduce 2 distinct asperity thresholds, and we get 2 distinct periods out of it. And we can look at the distribution of times between events. So this is for the very large events. They all happen at the same time. 40,000 time steps or so, you're going to get a big event. No questions. Now, for the smaller earthquakes, it's a little more complicated. There's a lot going down if you zoom in on that graph. You can think of this as noise, really. This spike here, that corresponds to the spacing between the blue shaded regions on that previous graph. So that's the period for the smaller asperity rate. Now, this research is still ongoing. The current hypothesis that we're testing is that if we bring the percent difference between the asperity thresholds closer and closer together, we're going to produce quasi-periodicity in the model. And if that's the case, we've introduced a parameter by which we can introduce quasi-periodicity, which is characteristic of real earthquakes. And hopefully, in conjunction with machine learning algorithms, we might be able to get some prediction going on. We shall see. I'd like to thank my advisor, Dr. Dominguez, very much. Without whom this wouldn't have been possible. She's great. Many thanks to Dr. McCase, Dr. McManus, and fellow surf student Jack Miller. They are all computer science wizards. I'm not a programmer, so their help was very, I can't overstate it. Thanks to the physics department for letting me take over the seminar room all summer. And thank you to VCIF and the SURF program for funding my research. And thank you all for listening. Are there any questions?